might be a little late. She's something with her kids.
That's okay. Adam, I'm seeing your question. Do we drop the lowest grade? The answer is no. But there are some bonus point homeworks, so I'm going to see how we do that. How I sort of, if you, some of you have been doing the bonus point homeworks, I'll check that out. Some of you haven't, and I want to make sure that you're not penalized. So I'll go back and make sure that we do that, get you that. But as far as dropping lowest grades, no, that's not something I do. Uh, that's not something I do. Let me say it that way. Jana, let me check it with you. Can you hear us now or something like that? Let me see. Oh, maybe so. Yeah, Adam, I have to admit, there may be something in the syllabus, but let me check it out because I was having some troubles at the beginning of the session. Because though I've been teaching math online for 20 years, I have not had to create a class in 20 years, in over 20 years. So that part of the creation was new to me as something I was behind on, and so I'll go back and check. Okay, question. So this question here says, hey, given f of x, find g of x and h of x such that f is found by composing g and h. In other words, this section right here says g of h of x, or g composed with h. The outer function first, outer function. The way that we read it is left to right, g composed with h, meaning h goes inside the g. So,
Sir,
mhm,
sorry to interrupt you, but are you recording this?
yes.
Cool.
Okay, let's see. Okay, I see what you said. Okay, so here this one says create a function f by composing two functions g and h with each other, putting h inside of g, such that neither g or h are solely the plane function x. They don't want you to make it, they want you to work for it a little bit, if you will. Okay, so the way that you go about doing this is take a look here. Notice, so remember composition is taking a function and putting it inside of a function, kind of like it's a cheesy example, but think about Taco Bell and they do like a burrito in a taco in a burrito, right? That's kind of what you're doing here. You're putting something inside something else. So the way that you go about this one, and not to say that I would probably do this on a test, but it's a good sort of mental exercise as to what you got going on, is take a look at the overall structure of this thing and really forget. What you want to do is just forget about forget about this part and notice it's just sort of a fraction, if you will. So look at where my point is look at where the variables are. In this function, we've stuffed the variable inside the denominator. So we want to think of what's the outer function, what's the bigger function, if you will. What are we stuffing? Or another way to look at it, what are we stuffing inside of another thing? And the way that this one works is sort of the overall structure is the big structure is a fraction, and we have this thing here, 5x minus 1, stuffed inside of a fraction, stuffed inside. So that's sort of the overall structure of the deal. So I would probably look at it like this, that the 5x minus 1 is being set inside of the burrito outside. So let the inside be this. Let the inside be that, okay? So I'm going to replace h of x with that inside part, just the 5x minus 1. Okay, so let's do that. Let's take this thing and rewrite it such that the denominator is replaced with uh, uh, h of x. Okay, so I would take this and I would say, well, this is 2 over h of x. Okay, and so remember, when you're doing composition, the inside function is becoming the input of the outside function. So in the outside function, so remember, well, when we do g of h of x, h is the inside. this h of x is taking the place of a traditional x, okay? Is taking the place of. So if I'm so kind of work yourself backwards then this thing is going to become our x. Oops. Is going to become our x. Sorry. So this time we're working backwards. We're going to pull that h of x out and replace it with an x. We're going to pull it out and replace it with an x. And this thing here is going to be g of x. So you take the overall structure and just pull out part of it. Okay, look at where the variable is, and basically wherever the variable is, that's what you're going to make h of x. So how about this? Does this sort of help out with this one?
Oh, hear me?
Go for it.
Can you hear?
Can you hear us, Jana?
Yes, can you hear me?
I can, yes.
Okay. I just hooked up a Bluetooth, but that's not what I'm asking. So I just heard you say we're going to pull out the part where the variable is. What if it was on the top? We would take it from the top, not
Sure.
from the numerator, not the.
You want me to do another one?
Um, yeah, you can. But I just wanted to know, like, if it was switched, if the 5x minus 1 was on top,
Mm-hmm.
would we pull it from the top versus the bottom of the fraction?
Yeah. So let's do another one right quick, just to kind of suppose we have a function. Oops. Suppose we have a function. Oof, terrible color. Pink. Terrible color. I may have to do red just because of the color contrast. Black it is. Sticking with black. Okay, so suppose I have a function like this. F of x equals, so a wholly new problem. 3 minus 4x, all of that over 7. Okay, so same sort of thing. We want to write it as g of h of x, so h is the inside function. So we're going to make the numerator, oops, we're going to make the numerator h of x. Okay, we're going to replace that part. So that means then that h of x is going to be that top part. H of x is going to be 3 minus 4x. So we'll write that off to the side. So we'll write that off to the side here. H of x equals 3 minus 4x. So then what does that mean that g of x becomes? Well, keep in mind, when we're doing g of h of x, the h of x is the input. So that originated as g of x. And so you replace the h of x with just a plain old x. So that means that it's x over 7. Does that help?
Well, I'll just have to. Are you recording this? I'll just have to go back to what I missed because yesterday my computer was so messed up, and um, I just got it working.
Okay.
So the g of x, um, when you say we're replacing it with the h of x,
No,
or how do we just?
the h of x is the input, is being inputted into g. So
Okay.
it's the input, and so you just replace it. You're working backwards in essence. You just replace it with plain old x to get you what the outer function is going to be for this. So essentially, what we're doing here is we're working the reverse process. Composition is taking a function and stuffing it inside of another function. Here, what they want you to do is they want you to unravel that. Given the result, given the resulting composed function, the result of it, the whole thing, unpack it, pull out. Composition is stuffing in. They want you to decipher and say, well, what were the original functions? That's what they're wanting you to do here.
Okay. And so we.
So my recommendation would be wherever you see the x, that's what's going to be the h of x. And so replace it with h of x, and then replace the h of x with a plain old x, and that gives you the outer function. Does that help to simplify it?
Yeah, that's better.
Okay. Should help you with the homework. Let me say it that way. Again, I'm not a big fan of this question. I want to know that you can compose, but I'm not much concerned about you being able to unravel. Composition is troublesome enough.
Okay.
Okay. So I'm going to call this the Taco
okay.
Bell. I'm going to call this the Taco Bell function. You're taking your taco and you're putting it in a burrito. That's what composition is really all about at its core. Okay, anything else on this one?
That's fine. That's good.
Okay, so let's switch over to, go back to the course. And let's pick up where we were on inverse of functions. And we started talking about what does it mean to be, why do we, inverses are special types of functions. So you have relations, which means you have any pairing of domain and range, and you can have things repeat. We don't like that. We do. That's fine. There's nothing wrong with them. But we like functions. And really, algebra is all about the study of functions. We love functions in algebra. So we have these relations where you can have any pairing you want, but we study functions where every member of the domain is paired with one member of the range. There's a subset, a special class of functions called one-to-one, where not only is every member of the domain paired with one member of the range, but every member of the range is only paired with one member of the domain. Think of one-to-one functions as kind of like being married. You only have one spouse. That is it. So in one-to-one functions is like being married. Every member has a unique domain and range have a unique pairing, and they're not paired with anybody else. That's one-to-one functions, the special type. If you're one-to-one, if the function is one-to-one, you have an inverse. And that's the cool part. Finding the inverse is actually pretty fun. It's not arduous. It's pretty straightforward actually. But it's fun. Let me say it that way. Fun. I mean, as fun as working with functions can be. Okay, let's see what we got. Okay, so one thing to quickly note here is when we're dealing with inverses, you will see an exponent, you'll see the function name with an exponent of -1. Now, it's not a true exponent. You're not raising anything to the -1 power. It is just simply indicating to you what you're dealing with is the inverse of another function. So this is saying here, this s to the -1 is just simply saying the inverse of s. That's all it's saying. No mathematics, no calculation, no actual exponents at all. It's just indicating to you, there's a function we call s, I'm the inverse of that. That's all it is. So first of all, so this one is already sort of assuming, by the way, that this is a one-to-one function, and it is, so we're good. I'm not going to go into the details. We'll see another example. This question focuses on, if you have a one-to-one function, how do you find the inverse? So let me kind of do it this way. Let me take this right here. I'm going to take this thing right here, and I'm going to write it not as ordered pairs, but I'm going to write it as those ovals, okay? So the S function has the domain of 7. Let's do 7, -10, -5, and 4. Okay. And then there's a range of 5, 1, 7, -1. And it just pairs this way. Okay. Pair. Okay. This is the domain. This right here, the left is always where the arrow emanates from is the domain, and where the arrow ends is always the range. Good so far? Questions on any of that? Now, this is our function. We're going to call this function the S function. Okay? And let me change the color ink. This is my S function. S function. Okay? So the question now is how do we find the inverse? And here it is. To find the inverse, you switch the domain range. Just like that. So what I'm going to do is this. I'm going to take my two circles, and I'm going to do this. I'm just going to turn them. So what does that give me? So I'm going to take my two circles. Oh, sorry. Take my two circles. Now I'm taking the range values and making them the domain. So domain becomes range, range becomes domain. You switch places. So 5, 1, 7, -1. And then take my domain values. That is a terrible circle, oval. Let's see if we can do it again. Well, not any better. 7, -10, -5, 4. Now this time the arrows, they still point from the domain to the range, okay? But look at the relationship. Oops. This is now the domain of the inverse function. Oops. So we're going to call this S inverse. To find when you're given ordered pairs or you're given this sort of circle thing, all you do is you switch the domain and the range. In other words, in the S function, the domain becomes the range in the inverse function, and the range in the domain in the original function becomes the domain in the inverse function. They switch places. Switch the domain and the range with each other. So in other words, I could have done this shorthanded, but I sort of wanted you to see the sort of switching process. So basically, you just, for the S inverse function, switch the ordered pairs around. Turn them around. That becomes 5, 7. Take this, switch them around. 1, -10. Switch, switch, switch. So then what's this ordered pair become? What does -5, 7 become?
7, -5.
7, -5, right. And how about the last one?
-1, 4.
Right. So when you're finding an inverse, all you do is switch the domain and the range. Memorize that. Because it's going to be the process. We're going to see this in another format, but it's going to be the same process. Switch the domain and the range. Let me pause here. Questions on anything so far? Okay, let's keep going. Let's see. Wait. No words. Okay. So find, this one says, find 4 points contained in the inverse. Express your values as an integer or simplified fraction. Okay. So what we have here is we have an equation of a line. Remember, this is an equation of a line. 2 variables, linear equation, okay? So how are we going to find 4 points? How are we going to find 4 points? How did we find? Remember, a line is composed of what? Ordered pairs. How did we find ordered pairs when dealing with an equation like this? Remember, a line is composed of infinitely many ordered pairs, infinitely many dots. So we can pick any number we want, and we will find a pair. Okay, so give me a number. So pick a value for x and find the associated value for y. So pick a value for x. Give it to me. Lay it on me. 0. Love it. So I plug in 0. So that becomes y equals -4 times 0 plus 1 gives me 1. So I'll put the 1 right here. Do it again. Give me another value for x. 1. Fine by me. Look at that. So we plug in 1 for y, 1 for x now equals -4 times 1 plus 1, and that's going to give me -3. So all we're doing is we're just picking values for x and finding the y value that's paired with it. Keep doing the process. What would we say? We need 2 more values for x because we need 4 points. So what value next?
We just go up the line, 2.
Fine by me. So that becomes -7, and that becomes -11. And so we're going to put, these are the ordered pairs, remember? They create x, y ordered pairs. So what are those ordered pairs? I'm going to type now. 0, 1, 1, -3, 2, -7, 3, -11. So now it says find the inverse of those. So what's the inverse of this ordered pair?
1, 0.
1, 0. Right. So the inverse then, I'll write it over here. The inverse is, so we have 1, 0. What else?
-3 and 1.
-3, comma 1. Right. Then -7, comma 2. And then -11, comma 3. Good. That's what we do. So I'm going to type that in now. 1, comma 0. -3, comma 1. Oops. Wait a minute. Sorry. Yeah, this is right. 1, comma 0. -3, comma 1. -7, comma 2. And then what? -11, comma 3. Let's see if we're right. Submit answer. Boom. We got it. So let's see what's next then. So now it wants us to find the domain and the range, okay, of the inverse. Find the domain and the range of the inverse. So remember, in the domain, when we're talking about the inverse, the domain is just, and the range have just switched places, okay? So what this question's really asking is, what is the domain and the range of the original function? What is the domain and the range of the original function? What's the domain and the range? What's the domain of every line? What does this look like? Just kind of picture it, if you will. This looks like this. So remember, domain is left, right. So what's the furthest left and the furthest right that a line goes? You really do have to remember, hey, this is a line. You want to remember that. It helps. If you didn't remember that, how else could you get it? Remember, the domain is All real numbers except for the ones that don't work.
Mhm.
So is there anything that doesn't make this thing work? Anything that creates a problem? No fractions, no square roots. So good. So those are our problem areas, fractions and square roots. If you don't have a fraction and you don't have a square root, the domain is everything, is everything. So all real numbers. Put squiggle R. The hard part sometimes is the range. That's hard. That's harder to read. Harder to read just from looking at the formula. And that's why you want to recognize this is a line. This creates a line. Remember, this is a linear. Y equals mx plus b creates a line. When you have an exponent of 2, that's a quadratic, a parabola, things of that nature. You want to remember those properties. So when we talk about the range of this function, lowest, highest, what's the lowest this function goes down to? This arrow says keep going down, 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 down.
Yeah.
To where?
Negative infinity.
Negative infinity. And this one says keep going up, up, up. To
Positive.
what? Positive infinity. So that means that what's the domain then? Negative infinity, positive infinity means the domain is what? Everything.
Yeah.
Real numbers. Now that's for this. This is the domain and the range for this function, that equation. For the inverse, you switch places. You switch places. Now, fortunately, they're the same. So when you switch places with them, it still becomes all real numbers. Oops. For both. But that's because the domain and the range originally, so they're the same thing in top and bottom. But the point is the process, you have to find the domain and the range of the original function and then switch them to get the domain and the range of the inverse function. That's the takeaway. And by the way, how would you write all real numbers at an interval notation?
Parentheses on both sides.
Okay?
Negative infinity,
Yeah.
comma, infinity.
Yep. Good. That's perfect. So that's probably how they want you to write it, by the way. So
Would it matter if you put the positive or the negative first?
yes.
It does.
Yeah, lowest always goes first.
Okay.
So I put the squiggle R for real numbers. That worked just fine.
Okay.
But you really do, things are coming together. They still, I sound like a broken record, but things are still coming together. You still have to refresh, be fresh on that other stuff. Y equals mx plus b. How do I get equations of lines? How do I get points? You have to you do have to, they want you to recognize that what you're dealing with here is a line. And remember the 4 orientations of lines: diagonal, diagonal, up, or flat. And that affects the domain and the range. It affects the domain and the range. So that's sort of one of the takeaways here. Okay. All right, now we're going to find the inverse. And for this one, I'm not going to do this one yet. What I'm going to do instead is I'm going to do an example, because I don't like this example. It's annoying. But we'll get a similar example. I'll show you the process. Hold on just a second. Do this, switch over. Okay, suppose I have a function f of x equals what? Give me something. 3y plus 2. I don't know. Just making something up. Not 3y. 3x. 3x plus 2. Okay, all linear functions, linear equations, y equals mx plus b. All linear equations and functions are one-to-one. and have an inverse. Guaranteed, all the time. All linear functions are one-to-one and have an inverse. So, how do you find inverse function? Step 1. Replace the f of x with y. Oops. Step 2. Solve for x, i.e. get x by itself. Step 3. Replace the x. Nope. Sorry. Yeah, I'll do this. Now replace the y with x and x with f inverse of x. How about this? Replace the x with f inverse. So let's see how we do that here. So f of x equals 3x plus 2. Take the f of x and replace it with y. Oh, whoops, I'm sorry. Forgot a step. Replace f of step 2, I'm sorry. Step 2, I knew there was something. Switch, remember, the inverse and the domain and the range of a function of an inverse is switched. So I forgot to do that. That's the thing I was, switch the x and y, solve for y, meaning get y by itself, and replace the y with, this is how it works. I knew there was something I was missing. So step 1, replace f of x with the variable y, the letter y. Step 2, switch the x and the y around, solve for y, and then replace y with f inverse. So let's see how we do that here. So step 1, take that f of x and just simply replace it with y. Cool so far? Step 2 is take that x and the y and switch them. You don't switch anything else. This is kind of like trading places, okay? What's the one? What's the mom? What's the other movie where mother and daughter or father and son switch places?
It's Freaky Friday.
Thank you. It's the Freaky Friday. So take the x, take the y, make it x, make the x, take the x and make it y. Freaky Friday step. This is the Freaky Friday step. They're switching places. Now solve. Step 3 says solve for y. Get y by itself. So take it from here. This goes back to your skills all the way back in unit 2. All the way, I'm sorry, week 2. How do we solve for y here? What's my process?
Subtract it from both sides.
Subtract what?
I'm sorry. Subtract 3y from both sides.
Subtract, I'm sorry, say it again.
I guess to make it easiest, subtract 2 from both sides.
I'd subtract 2.
Yeah.
So x minus 2 equals 3y, and then what?
And then divide 3y. Divide 3 on both sides.
Divide 3. So I'm going to write it as 3. So we get x minus 2 over 3 equals y. Now take the y. Now the last step says take y and replace it with f inverse of x.
Can I ask a quick question about that form, just how it's written? Is it replace y with f to the negative first power x?
It's supposed to be inverse.
Got it. Thank you.
Yes. So now I got it better.
Oh, cool. Thank you.
So this is the inverse function. So replace f of x with y. Freaky Friday, switch the x and the y. Solve for y. and replaced y with f inverse of x. Essentially, the inverse function is the opposite of the original function. How do I know? There's addition here. In the original function, it's 3x plus 2. Look at the inverse. Opposite. Subtraction. Here, the 3 is multiplying the x. In the inverse, it's dividing. So that's kind of a quick self-check. Now there is an ultimate way we can self-check. We're going to talk about that too. But this is the process for finding the inverse. Replace with y, Freaky Friday, solve for y, change it back to f inverse. So with that in mind, let's go back to the other one. Let's go back to the other one. I still have this here. So how am I going to find the inverse of this, of this function right here? Same process. Nothing changes. It's just a little weird. So take my v of x, g of x, f of x. It's all the same. Change it to y. Oof, hold on. That's giving me some fits. So y is equal to x to the 1/5 power plus 4. Freaky Friday, x equals y, to the 1/5 plus 4. Solve for y. How am I going to solve this thing here for y? Do the opposite. So get rid of that 4 first. How am I going to get rid of it? Opposite. Subtract 4 from both sides. So I get x minus 4 equals y to the 1/5 power. I'll tell you this one. The way that you get rid of an exponent like this, a fractional exponent, is just raise it to the reciprocal. So what's the reciprocal of 1/5? Just flip it to a 5. So raise both sides to the 5th power. Just like the square root and the square cancel each other out, we'll see more of that later. It's the same thing here. The 1/5 power is canceled out by the 5th power. So raise both sides to the 5th power. It's weird. I don't like it. That's why I don't like this problem. That's why I wanted to show you. So this becomes x minus 4 to the 5th power equals y. Now we replace y with the inverse. In this case, the inverse function is v inverse of x. And voila. I may give you something like this, but not with like a 5th power. I'd give you something more like what we did in the previous screen. But you have to be prepared because they give you these. So, questions on this one? On the process for when you have the formula, when you have the formula for the function, this is the process for finding the inverse. Replace f of x with y, Freaky Friday, switch x and y, solve for y again, and then replace the y with the f inverse notation.
Yeah. So when you want to get rid of that fractional exponent, and you multiply it by the, I guess, reciprocal fraction, just 5.
You raise it to that power, right?
Right. So doing that, so both sides. So you raise the left side to the 5th power, x minus 4 to the 5th power. So you don't also raise the y to the 5th power. It just kind of like disappeared.
It did. Why?
Does y to the 1/5 power, is that just equal to v?
So what happens to this side right here? Remember your power rule? Power of a power? What happens? When you have power of a power, you multiply the two. So 1/5 times 5, and that becomes y to the first.
Oh,
That's why they cancel. Now, so I did originally have this as y right here. I just replaced the y with v inverse.
okay. Thank you.
Let's see. Okay, find the formula for the, oh, this is what we did. Wait, find the formula for the inverse. Okay. So similar thing, similar thing. Uh, oh, yeah. So same process, same process. So replace f of x with y. Replace, and I'm going to change my coloring now. Replace x and y. Now this one, if you notice, what we can do, what we would do is cross multiply. Okay, because it's a fraction on one side equals a fraction on the other side. We would cross multiply. So we get x times y plus 1 equals -2. We're cross multiplying here. We're multiplying -2 times 1, the denominator of the first fraction with the numerator of the second fraction, and then we multiply this one right here, x, the numerator of the first fraction, times the denominator of the second fraction. So how do we get y by itself here? Remember, that's our goal. Well, what you can do is just first divide both sides by x. Get rid of the x. And so let me come over here now. That's y plus 1 over, oops, -2 over x, and then subtract 1 from both sides. This would be the answer. And it all hinges on this cross multiplication part of it. So I wanted to give you that answer is what I'm trying to say. So when you get another one like this, you can see, you have an example to sort of mirror on that.
So I see that you cross multiplied. So you got,
And when I cross multiplied, the cross multiplication was that. This was the result of cross multiplying.
right. Yes. Yeah, got that. And then I just the part that confused me is when we put it over an X.
So I want to get rid of this x. We can do a couple of things. We can distribute the x inside or whatnot, but you can, because it's x on the outside of a parentheses, it's x times y plus 1. So you can get rid of the x just by dividing both sides by the x, because you're going to cancel it. So you're treating the x like a plain old number. This is multiplying, so you can just divide both sides by that. It's the same thing. Let me say it this way. It's the same thing as if the x had been a 7. You could divide both sides by 7. The point at one of the takeaways, just to sort of recall from earlier, is that when you're solving for y here, everything else is treated like a regular number. So you can add it, subtract it, multiply, divide it. That's the thing you have to recall from way back a couple weeks ago, months ago now, where you're solving formulas you're isolating these variables in a specific formula. You're treating everything else as a number. And so it's the same thing here. X is treated as a number, and so to get rid of it, it's multiplying. The opposite is division. You don't like that way. Addie, you don't like my way.
Oh, I'm sure it's great.
What would you have done? Let me ask it this way. If you're sitting here in this step, what would you have preferred to have done? Because it's not what I did is not the only way.
Okay. Yeah, I guess I would have distributed. So
Nothing wrong
x,
with that.
y plus x equals 2.
Nothing wrong with that. Perfectly legitimate. So that becomes xy plus x equals -2. Now what?
Um, I guess, okay, so what are we trying to solve for again? Y?
Y.
So we could subtract x from both sides?
Subtract x from both sides. Love it. Perfect.
Alright.
Yes.
Okay,
Excellent.
so we have xy equals, should we put negative x or -2 first? -2
Whichever
minus
one,
x.
whichever one you want. I'll put -x first.
Okay, negative x minus 2. And then you'll divide by x on both sides. Okay, I see. Yeah, I'm gonna end up getting the same answer that you did.
You do.
Thank you.
It looks a little
Thank
different, but it is the
you.
exact same thing. You're right. -x minus 2 over x. It is the same thing. But
Okay.
the fact is it's the same thing. And so your way, just as legitimate as my way. If my way is not what you're jiving with, don't use it. Go with your way. You would have gotten the right answer too. And your answer is just as equivalent, just as good as mine.
Thank you. So the answer is just negative x minus 2 over x.
Right.
And you wouldn't, in this case, cancel out the x's, right? Because the negative x and the 2 are
Would not.
okay.
Would not. Good.
Thank you for letting me do that.
Sure. No, that's what I like doing it. Uh, what? Inverse. Well, this is weird. Okay, same thing. I'm not going to do this one, but it's the same things we did earlier. Get values of x and y and switch the ordered pairs. So but this is weird. There is no inverse. I don't know why they did this. This is not a function. It's not a function, and so there is no inverse function. This one's weird. I don't like this one. You can tell I have feelings about it.
I do too.
So
Is there a button that says not a function?
no, I don't know. Technically, it's wrong. I know what they're going for. They want you to be able to do stuff with different operations, and that's why it's the same thing. Pick a value. This one, though, instead of picking for x, pick for y, because y is in the absolute value. So pick 0, 1, 2, 3, like you did last time, but put it in for y, because it just makes it easier to do. Because the other reason is because x is already by itself. So make it easier on yourself. Pick something on the other side where all the junk is happening to it. All right, what's this one? Find the inverse. Okay, we can do it. That's fine. We can do this. So what they want us to do, so I'm not going to belabor this, but how do we, this is the function we're trying to find the inverse of, okay? All this is telling you over here, this is telling you what the domain is. This only works for x values that are larger than 1, or I'm sorry, -1. But that has virtually no bearing on the process for finding the inverse, okay? So it's really for this part of the problem, you would disregard it. It doesn't come in yet, okay? You're just focusing on this part of the problem trying to find the inverse of that. Same process as before. Switch. Oops, okay. So y equals x plus 1 squared. Let me get rid of this. X plus 1. My handwriting's getting bad. Sorry. X plus 1 squared plus 2. Switch x and y, so I'm going to switch my color ink. So x solve for x. So we first have to do what? When we solve for x, what do we have to move first? We have to get rid of that 2 first. So it becomes, I'm going to come over here now, x minus 2 equals y plus 1 squared. Now we have to get rid of the square. How do we get rid of a square? What's the opposite?
Square root.
Square root. You got to do it to both sides. Sorry, sticking. And so what does that give us? The square root of x minus 2 equals y plus 1. One final step. One final step. I got to get rid of this this plus 1. So I'm going to do that by subtracting 1. So this becomes, now I'm going to write it as negative 1 plus, just to kind of make sure I don't get crosswise. Hold on, my pen. It's 2. So the lesson here is, and what they're doing in all these examples is they're having you refresh your memory. What does it mean to be the opposite? How do you do the opposite? How do you solve equations? Do the opposite, do it to both sides, just in different contexts. So this would be the answer here. Any questions on that?
Why would we prefer the square root over the square?
That's just the thing. You remember, you're trying to, when you solve equations, you do the opposite. So the opposite of squaring something is the square root. That's how you get rid of the exponent of 2.
Right. I guess like my question was just why why would we prefer to get rid of the square and get the square root?
As
And
opposed,
then when we get the square root of both sides, we get rid of the square root sign from the right side, but we leave it on the left side.
yeah, that's because here the square root symbol and the square cancel with each other.
Okay.
Just like the square root of 4. What's the square what's the square root of 4?
2. It's 2 squared.
What's the square root of 2 squared?
4.
It's also 2.
Square root of 4.
So that my point is that the squares cancel, the square and the square root cancel to just pop out the thing in the middle.
Gotcha.
The thing inside.
Yeah.
That is the opposite. That's the way you would want to do this one. I mean, you could FOIL and do a bunch of stuff, but it will get you nowhere real quick.
That's probably what I want.
It'll get you to a dead end, is what I'm saying.
Okay.
Okay, so more of the same here. Find the inverse, find the formula of the inverse. Really nothing new at this point. Okay, determine if the following function has an inverse. Okay. So go through the exercise on this one. You're determining if it has an inverse. If it has an inverse. So go through the exercise of finding the formula for the inverse. So switch your x and y, solve for y, so we divide both sides by 3. And then to get rid of the opposite of taking the square root is squaring both sides. So this becomes x square, x over, oops. If we square both sides, let's just do this. X over 3 squared. And what they're asking you is, once you do this, is this thing a function? Yeah, it's a function. Is it a function? Yeah, it's a function. No, there's no problems with it. So G does have an inverse, yes. Sort of interesting. Anyways, yeah, so G has an inverse. That's the answer to this one. And the reason, remember when we're first approaching functions, remember something, when you're given the formula, the way to tell if it's not a function is if we had an exponent over the y. But because the y has just an exponent of 1 or no exponent written here, then it is a function, no matter what's going on the other side. It's the y that's determinative. So look at the y. If it's a y to the first power, yeah, it's a function. It's a function. Okay. So it's just more of the same at this point. I don't see anything. They're not doing the one thing that I thought they would do, so that's okay by me. Find the formula for the inverse. Determine if the following has an inverse. Okay, now this is interesting. This does not have an inverse. This does not. I can tell right away, and I'll tell you the answer, by the way, without even having to look at it. Squared. Squared. So let me kind of step back a little bit. Let me step back a little bit. And I'll tell you why this one doesn't, how we can just sort of know by looking at it. If we go back to this idea, oops, remember how we found whether something was a function or not? How did we go through that exercise? How did we determine that this graph is a function? What was the test, if you will?
Vertical line test?
Vertical line test. Right. Okay. That's if it's a function. That's if it's a function. Now, how do we know if it has an inverse? In other words, if it is what we call one-to-one. You don't know yet. When you're looking at the graph, the way that you can tell if it's one-to-one is not the vertical line test, but the horizontal line test. Draw horizontal lines through the whole thing. And the same thing, if it hits the graph in only one spot, then it's one-to-one, and yes, there is an inverse. Yes, there is an inverse. So not every function has an inverse. Oops. Messed up. So let me do this one. Does this have it? Is this a function? Does it pass the vertical line test? Yes, it is a function. Does it have an inverse? Does it pass the horizontal line test?
No.
No, fails right there. Fails right there, fails right there, fails in a lot of places. But it only has to fail in one spot, okay? And our first failure was it. Not a function. So how did I know? So this goes back to, what's the base function for this? Remember we talked about the transformations and all that stuff? What's the base function of this one? Well, it's a u. And what are all u's? This is the x squared function. All u's, anything that makes a u, is an x squared function. And that's how I knew this thing does not have a function. Because I said, oh, look, that's x squared. That creates a u. It fails the vertical line test. I'm sorry, the horizontal line test. That's what you should be doing too, is going back. Remember a couple lessons ago, what's the base function? What does the graph of the base function look like? And would it pass the horizontal line test? Will the base function pass the horizontal line test? And if the base function wouldn't, then whatever you're dealing with won't either. So I know because of this x squared right here, this is the base function, the base graph fails the vertical line test. So no, this one does not have an inverse because it fails the horizontal line test. That's what you want to do on this one. Connect the function with the graph of the base graph, and then from the base graph, see if it passes the horizontal line test. How about that? Let's see if we can get another one here. Awesome. This is one I was hoping to get. V of x is equal to, remember the vertical bars is absolute value of x. Does this one have an inverse or not? What does the graph v of x equals the absolute value of x look like? You don't have to plot it. What would it look like? How would you describe the graph? Is it a U? Is it an S? Is it a straight line? Is it something else? You take
Does this mean that it only has an x value, no y value?
No, remember, well, when you're dealing with functions,
No.
it is the y. This thing is the y.
Oh, right. Okay.
So this graph, absolute value, remember what the absolute value graph looks like. That's what you have to remember. They're actually telling you what it is. It's a V. The absolute value creates a V graph, a V-shaped graph. Comes down to a point and then shoots back up. So, based upon this graph right here, does it have an inverse or not?
No.
No. Right, does not have an inverse. Fails the horizontal line test. So those are the things you want to keep in mind. Kind of goes back a couple lessons. What's the base function? What's the graph of the base function? Linear functions are straight lines. Quadratics, exponent of 2 is a u. Absolute value is a v. Exponent of 3 is a cubit. It's an s sort of shape. So those are the things you want to keep in mind for this. Okay, so we've done that lesson. We did pretty good on that, I feel. Where are we at on time? Oh, we got about 20 minutes ish. Okay, so now we sort of make our final push, if you will, into everything. And a lot of this is going to be review of stuff that we've done in the past. So this sort of ends, if you will, our lesson on functions. 4.4 ends our lesson on functions. We will still see functions, but it's not going to be the heavy emphasis that we're doing here. We're just going to see uh, different things. Okay, so now we're going to get into more, and you'll see polynomials. We're going to be dividing and finding zeros. So essentially what we're doing is we're honing in on polynomials. Heavy, heavy, heavy. So that's the first part of it. Looking at polynomials and their zeros. Then we're going to take a look at what we call exponentials and logarithms. Exponentials and logarithms. They're inverses of each other. They kind of go hand in hand. Exponentials and logarithms, they're like cousins, you know. Anyways, so we'll take this up first, and then we'll take this up second. Now we're going to do this over the course of many days. So this will probably be Wednesday, Thursday, Monday, Tuesday, Wednesday, and then Thursday. Yeah. So this will be the remainder. So we'll probably do about 2 lessons at a time to kind of navigate our way to the very end of the whole thing. Okay, so let's take a look at polynomials and polynomial inequalities. Now, what do we mean by polynomials? You've worked with polynomials before. Let's kind of see. What in the world? Okay. So when we say polynomials, that's sort of just a way of saying no fractions, no square roots. Polynomial means no fraction, no square roots. But we can have exponents over our variables. Okay? So no fractions, no square roots, but we can have exponents. Now this question here asks us, does the value of x equals -7 solve the following polynomial equation? That's a lot of words, and we didn't need to say all those words. We didn't need to say that. When we say solve, what we're essentially asking is, in this particular question, does x equal -7 solve the following equation? We're asking is the value -7, is it a solution? Does it work? Does it work? And so let me step back. Suppose we had something all the way back from, the first week or two of class. Suppose we had something like this: 2x plus 1 equals 7. Okay, and I ask you, hey, I found this solution right here, x equals 3. Am I right? Am I right? Is that the solution? X equals 3? Your probably inclination is to solve this, go down the steps, and see if you get x equals 3. That's probably your inclination to do. But if we're asking, remember what we're asking, what we're trying to do is, we're saying that if something solved is the solution to the equation, what we're saying is it works. It works. Plug in, replace the value, the x there, with the value you found. So take your x of 3, plug it in, and simplify both sides down to a single number. So we get 7 equals 7. Does this result here indicate to us that 3 is a solution? Does plugging in 3 and then getting 7 equals 7, does that tell us that 3 is a solution?
Yes,
Why? You're right. Yes. Why?
because it's a true statement.
It's a true statement. That's what this question here is asking. Does it work? Does it give you a true statement? It's just like the one you did many moons ago now. So plug in the -7 for x, and simplify both sides to see if you get a true statement. So order of operations, exponents first, so -19 times 49 plus 4 times 7. 7 times 7 times 7. I don't know. That's -343. So now 19 times 49, or -19 times 49 is -931 plus -28. -1029 70. Whew, really making this work here. 903. Nope, that's not right. Negative 959. And what's this one? Negative 959. So, true statement. So this means that x equals negative 7 is a solution. Yes. You just take the value, plug it in for the variable, see if it gives you a true statement. If it does, then yes, it is a solution. Oops. Questions on that one? All right. Find the degree and the leading coefficient. Didn't we do something like this? Let me kind of gauge where you all are at. If we look at here's the function. What's the degree?
3.
You're looking in the right spot. That's good. That's what I wanted to see. It's been a while since we've done this. So the degree of a polynomial is determined by the highest exponent. So what's the highest exponent?
Oh, 2.
2. What's the leading coefficient? For that, you find the term that gave you the degree, and that term was this, 3x squared. And the coefficient, or the leading coefficient, is the coefficient of that term, which means the number in front of the variable, which is the 3 you were looking at.
Gotcha.
So let's see what they have in mind here. So degree is 2, leading is coefficient is 3. Submit answer. So what's next? Okay, describe, this is what, I knew there's got to be something. Describe the behavior of the graph as x, what does this mean? As x goes to infinity, and then as x goes to negative infinity. Okay, so let me show you what that means. Let me show you what that means. Let's get the graph. Here's the function, 3x squared plus 7x minus 8. What is the base function? What does it look like? Describe it. Straight line, V, S, or something else? That's what you should have a catalog. Straight
Oh,
line,
so
V, U,
if you have, is it
S.
is it a U because of the x squared?
Yes. That's what you
Okay.
want. That's the thing you want to have in mind. Okay? Straight line, V, U, S. Okay, those are the base functions. The basic ones. Basic. So this is a U. Does it have to be perfect? No. You just want to kind of draw a U there. Okay? It may or may not be the exact same thing, but it's going to take the form of a U. Don't know where, I can't tell you that, but it's going to be a U somewhere. Okay? So what this part is asking right here, as x approaches negative infinity or positive infinity, what that is saying is, so let's do this one first. Let's do the top one first. What happens to the function as it approaches negative infinity? Okay. So what you do is you start here in the center. Start here in the center, okay? And move your way x. Remember, x is horizontal. This is the x-axis here. So as x goes this way, what happens to your function? What happens to your range? Remember, this is the range. What happens to your y? G of x, y. So as the domain moves further left towards negative infinity, what's happening to the graph in the y direction? Is it going up or going down? As x goes this way, so as x goes this way, what's happening to the arrow, the blue arrow, as x goes towards negative infinity?
It continues going to the left for negative infinity.
It does, but what about the so
Mm.
when you're looking at the graph, the y component is the output of the function. The y component is the output, because remember, g of x is the same thing as y. G of x is the same thing as y. Y is f of x. Okay, so what this is asking here,
Would
what
it go
this,
because it's going to be negative infinity, so down is negative, up.
what this is, yeah, let me frame it this way. What this is asking is, as the domain goes to negative infinity, in other words, as you move left, put a dot. I can't do it, but put yourself on the center point and start moving left. You're not actually moving left. You're going to be traveling up this thing. Okay, if you were to walk along that path, as you moved in the leftward direction, the graph is steering you this way. Okay, so what you want to do then, what is g of x doing? What is the graph doing in the y direction? What's happening to the y's as you travel along on the left side of this thing? What would y'all say? Go up or go down or stay flat?
It well, the picture's going up, but if it's going in the negative direction, I would think it has to go down.
No, the x is moving in the negative direction. But what's the y doing? It's going up, shooting back up. So think of it kind of like this is a half pipe. For those of you who like do skateboards or watch motocross or something like that, you're going in this sort of, it's a bowl, if you will. So true, this is moving in the left direction, no doubt. That's moving in the negative. But the pairs, remember, think of an ordered pair here. You know, you have an ordered pair, right? I can't. It's hard for me to draw on these things because once I got a dot. But the y value is increasing. The y value is going up. It's climbing up the y-axis. Even though you're moving, even if you were trying to, you were moving that way, trace it. The y is going up. You see that? I got a bunch of arrows here, sorry. What it is you're just sort of imagining yourself sitting here on the bowl, on the bottom of the bowl, and moving in the leftward direction. And as you're moving in the leftward direction, it is lurching you up in this case. So the y component, the output of the function, the range, is going up the y-axis. As you move further and further left, you're going further and further higher. Just because you're moving in the left negative direction doesn't mean your output is negative. The output is the y-axis, what's happening to the y as you move left. That's what this is. I'm trying to find a way to articulate it more succinctly. As you move left, what happens to the y? And it's okay that the left, the x, is becoming more and more negative. You're just looking at what happens to the y, and it's shooting up. It's going to keep going up. So it's going to infinity. It'll never stop. What happens as x approaches infinity? As you go right towards infinity, what happens to the y? It also shoots up. So my point is, and one of the takeaways here is the graph actually tells you what the output is. It is the function, the g of x. It is the output. So you're essentially just watching. You're observing the shape of the graph. So let's do another one here. Try somewhere. Of course, it's the same thing. Oh, here's another one. So this graph here, what's the base of this graph?
It would be a U also.
But which way? Is it going to be, yeah, you're right. Is it a U that looks like this, or is it a U is it a U that opens up, or is it a U that opens down?
Um, I would say down because it's negative 4x squared.
Yes.
Okay.
It's been a while since we've done that one, so I'm super impressed. Pretend that's a U. Pretend that's a U. So as x moves left, as you go left, you start here at the, you're moving in this direction, but you're tracing along this. As you move further and further left, what's happening to your output, to your graph? What's it moving towards?
Going down.
To what?
Uh,
It's going to keep going down. That arrow says go on forever.
negative infinity.
Right. Keep going down to negative infinity. And how about as x moves, and how about if you move in the positive x direction?
It'll go to positive infinity.
Well, let's see. We're here.
Oh, yes, it'll still be negative because
Yep.
it's in motion.
Yep. So we're still pointing down. So it's still negative infinity.
Okay.
Good. That's how this one works. You got to look at the base graph and then ask yourself what happens, which way do the arrows point as you go left, as you go right. Cool?
Got it.
Not too bad. Not too bad. It's just trying to, break it down, if you will. Get there. All right. Oh my goodness. Find the solution of the problem. Express your answer as an interval notation. Hmm. Find the solution of the polynomial equation. Okay, we'll do it. Okay. Let's step back. Remember when we just had quadratic equations? And we were solving quadratic equations and we said, hey, if you have two numbers that multiply with each other to give 0, what do you know about A or B? If two numbers multiply to give 0, what's A or what's B?
One of them has to be 0.
One of them has to be 0. That is exactly right. Okay, either A or B or both. Okay, they both could be 0. It's the same idea here. How do we know that? Is because this is x times x plus 2 times x minus 3. You have three numbers you're multiplying. Three numbers you're multiplying. So what is this saying? We have three numbers we're multiplying. What's the result it gives us? When it says less than or equal to 0, it's saying 0 or negative. 0 or negative, because that's what less than 0 is. These are negative values. So they want to know, what's the solution to give me something that's 0 or negative? It's the same idea. Take the three things and set them less than or equal to 0. What things will give you negatives, in other words, or 0 or negatives? So this one's already done. How about this one? What's the solution?
-2.
X is what? Equal to, greater than, less than what?
Less than or equal to.
Right. Good. 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 So I just want to see if you remember your inequalities. Good. And then how about this one? We add 3 to both sides, and we get x is less than or equal to 3. So now we have to write this as an interval notation. Okay. So, but before we get there, is there overlap between these solutions? Is there overlap between these solutions? So let's look at the number line. Well, if I'm a value, so remember this is 0, here's 3, and here's -2. This one here says I want all values to the left of -2. This one here says I want all values to the left of 0. Okay. And then this one here says I want all values to the left of 3. Is there one of these intervals that captures all of them? In other words, do we need 3 separate intervals, or does one interval work? Will one interval capture all the solutions?
Yes.
I would say 1.
Which one, the green line, the blue line, or the pink line?
I'd say the
The
green.
green line.
The green line captures them all, right? So if you're a solution to the green line, you're a solution. You'll get what we need. Okay. So what's the interval for the green line? How would we write it as an interval?
Um, we put the like square like parenthesis
Okay.
and then put 3.
Okay.
Uh,
Remember, it's smaller, comma, larger, left, comma, right, smaller, comma, larger. So what's the smallest value we can be?
all right, so we put a regular parentheses with negative infinity and then comma 3 with the square.
Boom. That's it. That's what goes here. That's the answer. So we don't need 3 separate intervals. We just need the one that works. One captures them all for this one. Cool? Feel good? Not too bad, I hope. Oh. Right, sorry about that. I lost connection. Hold on just a second. Okay. Okay, so this is probably a good time to stop because my internet's sort of weirding out. And it's time. I see it's 6:35. So we'll pick up with this in the next one. But keep going forward. You're doing great. Send me those questions. I appreciate you all sending those questions, and hope you have a good rest of your night.
So much. Have a good night.
All right, you too.
Bye bye.
Just one question, Dr. Andrew.
Uh-huh.
I mean, Dr. Harvison. I
Yeah.
mean, Professor Harvison. I'm sorry.
Oh, you're good.
Okay. For the skills, I
Mhm.
can email it to you, or
Yeah, let's actually go to the class on that. So you should be able to click on the assignment.
mm-hmm.
So let's say skill review here. Let me go as a student. Okay, so click on it,
Mm-hmm.
and then you see upload. You can
Mm-hmm.
either you can either type right in there. You can type it
Uh-huh.
if you want, or you can upload a document.
I can take a picture and just put it there.
Yep, there it is.
Okay. Okay. I'm about to send them now.
Okay, good, good.
All right.
Yeah, Tiffany, go for it.
Do we have class tomorrow?
Yes, that is a
Okay,
day. Yes, I'll be here. Let's say it that way.
okay, because
Some of
I
y'all,
have like a Thanksmas thing going on tomorrow around the same time as class.
I'll record it.
Okay,
Okay.
thank you.
All righty. Hope you have a good one.
All right. See you later.
Okay, have a good one.
Thank you so much.
Yep, yeah, glad to help. Glad to help. Appreciate. Keep it coming.
I really appreciate you.
Alrighty.
Have a good night.
Okay. Bye bye.